Hello and welcome back to Psychology 301 Learning. This is Dr. Williams and this is the fourth lecture on stimulus control. Today we're going to be talking about testing Spence's theory of stimulus control and discrimination and peak shift. So if you recall, Spence's theory basically made two major assumptions. The first was that gradients develop naturally because we have an innate ability to discriminate within each continuum. So whether it's color or shades of gray or tones or line orientations, whatever that continuum is, he argued that critters were born with the ability to tell individual stimuli in that continuum apart and that no learning is required. He also stated that peak shift is caused by overlapping excitatory and inhibitory gradients. The excitatory gradients centered on the S plus and the inhibitory gradients centered on the S minus. And so he argued that peak shift isn't even really a shift. It's really the result of response competition between these two overlapping gradients. And the S minus gradient inhibits or suppresses responding on the from the excitation related to the S plus gradient where they overlap. And there's a larger peak shift when the S plus and the S minus are more similar to each other. So Spence's theory regarding generalization gradients wasn't actually tested or directly tested until the 1960s. His idea that competing excitatory and inhibitory gradients were responsible for peak shift really hinged on the idea of whether you could actually measure an inhibitory gradient. Was there any independent evidence of an inhibitory gradient? And it took until 1963 for Honig, Pennypacker, and their students to conduct that line orientation study where they could actually see the inhibitory gradient. And so because of, in particular, because of that one study, but other studies as well, this part of Spence's theory is accepted as the best explanation for peak shift. It's received a lot of support, and so it's basically the main way we explain the peak shift phenomenon. Now, similarly, Spence's theory that generalization gradients develop naturally due to an innate ability to discriminate within each continuum at the time was met by opposition by Carl Lashley and one of his students, Wade, in 1946. And they argued that the ability to perceive differences within any continuum is not innate, that discrimination training or relevant experience is necessary before you'll get a peaked gradient. They argued that peak gradients developed in those single stimulus training studies because the subjects had already learned to perceive the differences in the continuum. So when they were being tested using colors, they already had experience with color. They had already learned that orange is more like yellow than red is, and green is more like yellow than blue is. And so the animals had already had enough experience with colors or with lines or tones or whatever was being tested because they had learned to discriminate before the experiments were ever even conducted. But just like the previous one, this alternative theory, this alternative perspective remained untested for years. So in 1962, Peterson conducted what I consider to be perhaps the coolest experiment in all of psychology. Why? Because he used ducklings. I mean, come on. Rats and pigeons are one thing, but ducklings are awfully darn cute. All right, so the ducklings were actually hatched and raised in the laboratory. And he divided them into two groups. Group one was raised in a monochromatic sodium vapor light environment. And group two was raised in a normal broad spectrum light environment. So what is a monochromatic sodium vapor light environment? Well, that's why I put this picture down here. This is a picture of what a street looks like at night when the street lights are on. And street lights are monochromatic sodium vapor lights. And you'll see what they do is they wash all the color out of everything. and everything in the picture is amber colored. These lights are amber colored, and they cast an amber glow on everything. It kind of washes everything out. So the street looks amber, the concrete looks amber, the walls of the buildings look amber, the poles look amber, everything, even the trees look sort of amber colored. And so they sort of wash out all other colors. So the ducklings raised in this monochromatic sodium vapor environment basically only ever see the color amber. Whereas the group 2 is raised in just a normal broad spectrum light environment, they see all colors from the time they hatch. Well, once the ducklings are big enough, they're trained to peck at a key light to earn water. And of course, the color of the key light is amber. So the little ducklings in group 1 basically live in an amber environment, and when the key light lights up, it's amber colored, but they can see it light up, and they learn to peck at it for water. The other ducklings in group 2 see all different colors, but when the light comes on, it looks like a yellowish amber color, and so they peck when it comes on. And then they're tested for generalization using all the colors of the color spectrum. So after they've learned to respond to this key light to peck at the key light, the amber key light, for water, and they do it reliably for a long period of time, they then introduce all the colors of the color spectrum on the key in random, many times in random order. And so for group 2, they've seen these colors before, but this is the first time they see them on the key. And for the ducklings raised in the monochromatic sodium vapor light environment, they now see color for the first time. And the hypothesis is that if Spence is right, Spence said, if the ability to discriminate color is innate, then they shouldn't need experience with all the colors, that they should still produce a standard peak gradient with a peak over amber because that's what they learned. Lashley and Wade, on the other hand, would predict that if the ability to discriminate color is not innate, then the ducklings should produce a high flat gradient. They should treat all the colors the same. In other words, whenever the light comes on, they should respond to it because on means that water is available. And yes, they learned it with yellow, but whenever the light's on. So it should basically be an on-off discrimination, and it should be, they should treat them all the same, so it should be flat, but it should be high because the light is going on. And so let me show you the data. Here are the data. Guess what? The one at the top, A, are the ducklings in group 1, the monochromatic sodium vapor light environment. And if we average all of these together, there's a little bit of variability for each bird, but they're all very high, and they are, relatively speaking, not statistically different from each other at any point. So you get a high flat line averaging across birds. And even if you were to average within birds, it would still be a high flat line in terms of the best fit line. So, and then down below on gradient B, we have the 2 remaining birds that were raised in the broad spectrum light environment, and they produce a high peak to gradient, just as would be expected. So, so clearly Lashley and Wade were correct, and Spence was wrong. And so, except that the one criticism of this study is that these 4 birds, because they're raised in such a strange visual environment, could have been colorblind. So Peterson actually took these same 4 birds and put them in the broad spectrum environment for an extended period of time. He then went back and retested them, and all 4 birds produced a peaked gradient. So they were not blind. They simply didn't have, they didn't have the experience that they needed in order to produce a gradient. Only after they got the experience were they able to produce the peaked gradient. So the conclusions are basically that Kenneth Spence's theory regarding the overlapping excitatory and inhibitory gradients to explain peak shift has received extensive scientific support, and it's accepted as the most accurate explanation of peak shift. However, his belief that within stimulus discrimination or within continuum discrimination is innate appears to be false. So the question is discrimination training necessary for a peaked gradient to develop? Well, based on Peterson's study, you would have to say yes, but I would say that the answer is that it depends. So the answer would be yes, that sometimes discrimination training is required, particularly if the organism has no experience discriminating along a particular dimension. So if they don't have experience with color or tones or lines, whatever that dimension is, then explicit discrimination training might be necessary before you could get a peaked gradient. The reason I put this picture here is because I wanted to give you a real-world example of this. So these are paint swatches from the paint store, and if I were to ask most of you what color they are, if I crossed out the little colors and asked you what color are they, and I held them up one at a time, you would say that one's white, and that one's white, and that one's white, and that one's white, and you would do it over and over and over again because they all look white. So, and the reason is that we don't have sufficient experience with these specific differences. The difference between heron white and simply white is so, it's such a difficult discrimination that we don't respond to it because we just don't have the experience. On the other hand, sometimes discrimination training is not needed. If an organism already has the experience discriminating along a dimension, like colors or tones or lines, then you probably don't need any further discrimination training. A peaked gradient will develop based on their previous experience. So I can take the same paint swatches and give them to a professional house painter and hold them up one at a time and say, what color is this? And he will say, oh, that's white heron, that's white dove, that's Swiss coffee, that's simply white, that's alabaster, that's white ice, that's Navajo white, whatever. So they would actually know the colors, and they look very different to them because they have that experience. And so that's the difference, is discrimination training, it depends. It depends on whether you already have the experience or not. If you do, you probably don't need further discrimination training, but if you do not, you might actually need explicit discrimination training in order to learn the differences before you'll get a peaked gradient. Now, before I finish, I want to just very quickly talk about some other factors that influence stimulus control, and in particular, I want to talk about belongingness. So, is it easier to learn about a discriminative stimulus, an S+, if it shares a relevant biological relationship with a specific response or with a specific reinforcer? So I want to talk about a study by Forey and Lolordo from 1973. They tested two groups of pigeons, and both groups have the same S+ stimulus, and they are required to perform the same response. In both cases, the S+ is a red triangle on the key paired with a tone, so it's a compound stimulus. It's a red triangle is the visual component, the tone is the auditory component, and it's the same for both groups. And the response is a treadle press. So the treadle is like a little gas pedal that's on the floor of the chamber, and the pigeons have to step on it in order to earn food. So they walk over and they put their foot on it, and they earn food. Now, the reinforcer for group 1 is food, and this simulates a foraging scenario. Okay, so this is sort of like behavior systems. Here we have a foraging scenario. They're earning food in the presence of a red triangle and a tone when they press the treadle. Group 2, the reinforcer is shock avoidance. So this is a predatory defense scenario or avoidance scenario. They're avoiding shock. So the red triangle and the tone come on, signaling that shock is coming. They press the treadle and the shock is avoided. And they're trained until they have good control by the S+, so that they're responding reliably in both cases. They're then tested for stimulus control by the components of the compound stimulus, so by both the red triangle alone and control by the tone alone. And what you find is that group 1 responds a little more to the light and little or not at all to the tone. And this should say group 2, sorry. Group 2 group 2 responds to both the light and the tone, but slightly more to the tone. And so here are the data. The bold black lines are the compound stimulus together, the tone and the red triangle light together. And these are two different groups of birds, so the rate of responding is a little bit different. But you'll see that the maximum amount of control for both groups occurs when the tone and the light are presented together. However, when they're tested separately, the tone is on the left, the light is on the right. So here's the food reinforcement group. The mean number of responses for the food group is very high for the tone and very low, almost 0 for the tone. So the light is here. They respond a lot to the light and not to the tone. The shock avoidance group, on the other hand, responds a lot to the tone and less so to the light. They do respond to both, but they respond twice as much to the tone as they do to the light. So the question is, what's happening? Group 1, the food group, in the foraging scenario, the light controls their treadle pressing behavior. Group 2, the shock avoidance group, the tone controls their behavior better. And the type of reinforcer determines which part of the compound stimulus controls behavior. The question is, why? Hello, CJ. That's my bird. All right. So Forey and Lordo would ask, why might the food and the light go together? And why might predators or predator avoidance and sound go together? And the trick here is to be the pigeon. Be the pigeon. When pigeons forage, what happens? What cues, what signals food? Usually it's a visual stimulus. They see something. They either see the food or something related to food. So they rely very heavily on vision. And so when going through this process, they are exposed to the light and the tone. They respond more to the light because a visual stimulus is much more likely to be paired with food than an auditory stimulus. Pigeon's food doesn't make a whole lot of noise. You know, ooh, don't eat me. Doesn't do that. So it's not like Horton Hears a Who. So food and light clearly go together because pigeons find their food with their eyes. On the other hand, pigeons are prey species, and so they're constantly vigilant, observing in some way for predators. And because they have to use their eyes to find food, they rely more on auditory cues to warn them about predators. Primarily because hearing a predator before you can see it is probably a good idea. If you have to wait till you see it, it could be too late. So although they will use both hearing and vision to detect predators, they rely primarily on hearing, on sound. And so predators and sound go together. And so we get this pattern of belongingness in stimulus control in terms of it creating overshadowing. For the birds in group 1, the light overshadows the tone. They don't even pay attention to the tone. All of their learning is dedicated to the light. Whereas in group 2, the tone overshadows the light to a certain degree, but they do learn about both. They learn twice as much about the tone as they do the light, but they do learn about both. So what we're seeing is overshadowing that comes as a direct result of belongingness. All right, I'm going to stop there, and we'll start up with our next series of lectures on extinction. Have a great day.